Hello, my name is YUEHAN. My project is about predicting adult income levels using machine learning. The primary machine learning task is binary classification. The target variable is income. Class 0 means income at or below 50,000 US dollars. Class 1 means income above 50,000 US dollars. The objective is to compare three machine learning models and recommend the most suitable final model. The dataset using in this project is a Kaggle adult census income dataset. The original dataset documentation is also available from the UCI machine learning repository. The dataset contains 32,561 records, 14 predictors, and 1 income target. It is suitable because it is public, real-world, and includes missing values, class imbalance, mixed data types, and future engineering opportunities. The notebook is organized into clear sections, including data loading, data cleaning, exploratory data analysis, future engineering, model development, hyperparameter investigation, and final evaluation. First, I import the libraries required for data processing, visualization, and machine learning. Pandas and NumPy are used for data handling. Matplotlib is used for visualization. Scikit-learn used for processing, model training, and evaluation. XGBoost is used as a third classification model. In this section, I load the adult census income data from the Civic SV file. The original dataset contains 32,561 records and 50 columns. These columns include 14 predictors and 1 income target. The first few rows are displayed here to confirm that the dataset was loaded correctly. Next, I inspect the structure of the dataset. The output confirms that there are 32,561 entries and 15 columns. The dataset contains both numerical and category variables. This mixed data structure means that different processing methods are required for different columns. The initial inspection identifies 24 exact duplicate rows. It also shows that the target class is imbalanced. Most records belong to the income at or below $50,000 class, while a small number belong to the income above $50,000 class. Therefore, accuracy alone is not sufficient for model evaluation. In the cleaning stage, I standardize the column names and remove unnecessary spaces from test values. The question mark symbols are converted into purple missing values because they would otherwise be treated as normal categories. I also remove 20 for that duty-like rows. Occupation and work class each contains more than 1,800 missing values, while native country contains 583. This figure shows the cleaning target distribution. Approximately 76% of the records belongs to the lower income class, while approximately 24% belongs to the higher income class. Therefore, accuracy alone is not sufficient. I also use record, F1 score, ROC-AOC, and PR-AOC. The age distribution shows the higher income group is generally older. However, the two distributions overlap, so age cannot determine income by itself. This nonlinear pattern supports the creation of an age group feature. The education figure shows a clear ordered relationship. Higher education categories generally have a higher proportion of records above $50,000. Therefore, education number is retained as an ordered predictor. However, this is an observation and not proof of causality. Occupation also contains useful predictive information. Inductive, marginal, and processor specialty occupations have higher positive cluster rates, while some service occupations has low rates because occupation is a nominal variable. I use one-hot encoding rather than numerical labels. The capital activity feature shows the large differences between records with and without report capital activity. This supports the creation of binary has capital activity feature. The correlation matrix shows the education number has a clearly positive numerical relationship with income, followed by age, working hours, and capital gain. However, no numerical predictor has an entry strong linear relationship. This supports comparing a linear model with tree-based models that can capture nonlinear patterns. Based on the exploratory analysis, I create several new features. Each group represents different career stage. Work intensity separates part-time, standard, and long working time. Has capital activity captures whether capital gain or capital loss is non-zero. The signed logic capital features reduce the skew while presenting the director of the net amount. I also create a border metal group. I use one common 80-20 train test split for all tree models. Satisfaction maintains the same class proposition in both datasets. Render state 42 makes the experiment reproducible. Numerical missing values are imputed using the median, and the numerical features are standardized. Category missing values are represented by the unknown category, and the categorical variables are one-hot encoded. These steps are placed inside the modeling pipeline, so processing is weighted only on the training data. That reduces the risk of data leakage. I measure the impact of the feature engineering using the same logical regression settings and the same cross-validation strategy. The mean F1 score increases from approximately 0.684 to 0.695. The mean ROCOC also increases from approximately 0.908 to 0.915. Therefore, the engineering feature set is used for final models. For logistic regression, I investigate the regulation parameter C. C equal to provides the strongest validation result. Unnecessary model flexibility. For random forest, I investigate maximum tree depths. Unrestricted depths produce a higher validation F1 score, but it also creates a large training validation gap. For XGBoost, I test the maximum depths of the 3, 5, and the 7. Depth 7 achieves the highest validation F1 scores and ROC-AUC with a smaller outfitting gap than random forest. Therefore, depth 7 is selected. This table presents the final results on the common field of the test set. Random forest achieves the highest accuracy and precision. However, XGBoost achieves a higher recurse F1 score, ROC-AUC, and PRUC. Its F1 score is approximately 0.71, and its ROC-AUC is approximately 1.922. Therefore, XGBoost provides the strongest overall balance for the mineral class. The confusion matrix shows the actual prediction errors. XGBoost identify more higher income records and produce fewer false negatives than random forest. The cause is a large number of the false positives. For this project, records and for one score are practice test because the positive class is underrepresented. The RC covers compares the ranking ability of the three models across different neighborhoods. All three models perform clear above the random baseline. XGBoost achieves the highest ROC at approximately 0.922. This table compares the training and test performance. Random forest has the largest F1 gap, including more overfitting. Logistic regression has the smallest gap, but low test performance. XGBoost provides a better balance between predictive performance and generalization. The future importance feature shows that multiple group relationship, age, capable information, and education are important to the XGBoost model. However, future importance does not represent causality. The diagnostic group analyzes differences in recall and false positive rates between the recorded sex groups. This does not prove that the model is fair or unfair. A real deployment will require more detailed fairness analysis, stakeholder review, and legal and ethical checks. Based on the complete evaluation, XGBoost is recommended for the experiment. It provides a strong balance of the recall from ROUC and PRUC, with better generalization than random forest. However, this recommendation applies only to historical academic dataset and not to high-stake decisions about individuals. I will now present a final conclusion. In conclusion, XGBoost is recommended as a final model. It achieved an F1 score of 0.708. Its recall was 0.846. Its ROC-AUC was 0.922. Its PR-AUC was 0.822. Random forest had a slightly higher accuracy, but XGBoost performed better for detecting the higher income class. However, the dataset is historical and includes sensitive demographic variables, so the model should only be treated as an academic intelligence system. Thank you.